Great, thank you. Yeah, so thank you for the introduction. I'm a lead engineer in product development at Powerphotonic. We're a optics manufacturing company based in Scotland, just outside of Edinburgh. Um, we make freeform optical components, and today I'm going to talk a little bit about our beam shaping optics for optimization in laser welding. So I don't think I need to convince this audience that why we're using laser welding for manufacturing electric vehicles. But even with the advantages of laser welding, there are a number of challenges presented by welding electric vehicle components. Things like the weld geometry and welding of dissimilar materials mean you really need to optimize your process. There's a number of parameters you can play with to get the best performance out of your weld, either from the laser side or from the side of how you deliver that energy to the workpiece. With beam shaping, you're really pushing that beam delivery to its logical limits and putting the power exactly where you want it to be. So on the right here, I've got some example outputs from uh, beam shaping options that we've manufactured at Powerphotonic. So we've got sort of standard homogenizers where we can get a uniform flat top, either circular, square, or whatever geometry required. The increasingly common rings or core and ring geometries. We can also do rectangular shapes, or in the bottom right here we have some of that are more unique to us. We have asymmetrical beam shapes. So as we've heard today already, there's a number of ways you can do beam shaping. There's optical methods, in-fiber methods, coherent beam combination. Um, well, Power Photonic, the way we do beam shaping is with refractive optics. So there's an example here on the left. These are thin plates with a shallow machine surface on them. They're very low footprint um, into your optical system. So on the right here, I've got a basic outline of your optical setup. If you have a laser source, collimating lens, and focusing lens, this is an additional plate that you slot into your optical train, and somewhere in between your source and your focus, and it'll generate the shaped profile at focus. The incident light's refracted. The surface is finely controlled to impart a specific divergence to your laser beam, and that adjusts the shape of the profile that you get as the output. A little bit on our manufacturing process. So we have a laser-based manufacturing process that's been optimized for fused silica. Starting with a flat substrate, ablation produces the large-scale structure of your optic in a point-by-point manner. And then afterwards, the surface is laser polished. This reflows the surface and produces an optically smooth finish. This means we retain the bulk properties of fused silica. We have high power handling and low surface roughness, which means low scatter. This point-by-point addressing of the surface means that we have truly freeform optics. It lifts a lot of the conventional restrictions on optical manufacture, where you might need rotational symmetry or mirror symmetry. We don't have any of that, so that gives us a huge amount of flexibility in terms of what outputs we can generate. So there's some examples here of we can make flat tops, we can make beam splitting outputs with multiple spots, the core and ring, and then this tail shape output, which is an asymmetric one I'll come on to in a minute. In terms of how you install these into a practical system, for R&D trials, we've had some good results so far by replacing a protective window with one of our optics. So these process heads will typically have at least one protective window somewhere in the system. We can remove that, replace it directly with an optic of the same geometry to generate the beam shape as the output. This is good for a quick test. Might not be practical for a full manufacturing system. These really aren't sacrificial components, and you don't want to treat them as such. But for a more permanent installation, we've got an example here on the upper right, where we have a tray that sits into a low profile module, where you can add the beam shaper or remove it as needed, or swap the beam shaper to generate different outputs. This module could sit anywhere within the process head. We typically prefer it to be in the collimated path, but it's just as another design consideration to mount it somewhere in the diverging or converging positions. And similarly for a scanning head, if you've got a Galvo scanner, we would mount this somewhere before your scanner, ideally in the collimated path. So moving on to some actual beam shapes, the core and ring shape is becoming quite commonplace. There's a number of ways to generate this and a number of solutions out there already. Something quite specific to our method of generating this is we get a long depth of focus. So you get a core and ring caustic, not just a core and ring profile. We've this here is our simulated results with focal position in the middle, before focus and after focus. That core and ring is maintained, and then we have a measured version here as well. So we get good agreement between simulation and measurement. We've done some application trials with this for welding of aluminium 6082 in an autogenous manner, so no filler wire and no shield gas. And this high-speed video here is the welding, well, not real time, in slow motion. So we see improved melt pool stability during the welding. There's a reduction in the amount of spatter coming from this core and ring beam. And the headline result from this is that we got nearly a 50% increase in the tensile strength of the material after the weld was done, compared to welding with no beam shaper. Moving to something more unique to us, we have this tail, what we've been terming the tail shaper output. So this is an asymmetric beam that's been tailored to match the asymmetric nature of the welding process. So we have this linear shaped spot that would translate in the direction of the weld. You have this high intensity spot here that's still generating the keyhole and performing the weld, and a lower intensity tail that follows it behind. Again, we've got good agreement between what we simulate of the intensity profile through the beam shaper versus what's measured in reality. And here we've got some screenshots from the high-speed video of where we have no beam shaping. You get this round keyhole, and with the tail shaper, you get an elongated keyhole and a trailing tail behind it. These particular trials were done in an aluminium alloy, and we also have some similar results from simulation that indicate that this elongated keyhole from the asymmetric profile reduces the probability of seeing porosity within the weld. So there's some examples on the right here. The unshaped beam, you get these large pores left over from air bubbles trapped in the weld, and we don't see the same effects with the tail shaper. This set of results is the last set I have today. This is a customized beam splitting optic that we developed, where we've aimed to have a 3-spot output with the two of the spots trailing the main spot with 50% intensity, 50% of the intensity. And these would be separated laterally either side of the weld. This shows a strong influence on the weld's geometry, on the geometry of the weld seam. So here on the left, this is the case with no beam shaping, whereas when we have these additional spots, the width of the seam at the top is much wider. But also you can see there's a variation in the profile, so it peaks here in the middle. And if you reverse the direction of the beam shaper so that the 2 spots lead the main spot, this shape changes as well. So directionality is important, and we can have a strong influence on the cross section. So to conclude, I think I've demonstrated that these refractive freeform beam shapers provide flexible intensity patterns with simple system modifications. It's a straightforward addition of a single extra optical component. And the intensity patterns can be tailored to affect key parameters in the welding. What we can do for you is provide beam shaping optics and highly customized freeform intensity patterns to enhance various processes. And what we're looking for from others is to be presented with the challenges seen in laser applications, so that we can collaborate on optimizing these intensity profiles for a specific application. Just to finish, I need to acknowledge that as an optics manufacturer, we don't have capability to do welding in-house. So these trials have been done with some of them with Fraunhofer IWS, and some of them with WMG, with Pasquale's group, who we've just heard from. So thank you for your attention. I'm happy to take any questions.